So we looked at the role of alloying elements during solidification of the weld pool in a typical trip steel composition. We looked at two important alloying elements that are added in trip steel to stabilize retained austenite, the silicon aluminum. So the silicon aluminum additions to the material chemistry, it's leading to the formation of non-metallic inclusions. So we looked at because of the highly oxidizing nature of aluminum silicon, and you end up forming aluminum oxide and silicon oxide inclusions even before the onset of solidification. So once the aluminum silicon solidification, the oxidation happens, then subsequently the formation of aluminum oxide and silicon oxide attracts the other alloying elements such as manganese and sulfur epitaxially, enriching the surface of these oxides, leading to the formation of very complex non-metallic inclusions. So once you have a formation of inclusion, it can be made into our own benefit. For example, as I already explained, the inclusions are also act as a potential nucleation sites for when the nucleation of acicular ferrite. So if you favorably modify the size and volume fractions, and you may also improve the mechanical properties of the welds by nucleating acicular ferrite, and subsequently when you form austenite in the weldments upon solidification. And if you form a very bulk large inclusions of the non-metallic inclusions, you would expect material property, the weld metal property deteriorate significantly. So therefore, it is very important to control the environment, especially the presence of oxygen during welding. And if you use an GMAW, the use of a proper shielding gas, as well as the atmosphere protection of the liquid melt, it's extremely critical in controlling the size and volume fraction of these inclusions. And we also looked at the partitioning effect of aluminum to delta ferrite. So when you have an aluminum in the order of 1.1 weight% in steel, so the aluminum partitions to the solidifying delta ferrite, whereas all other alloying elements would tend to segregate towards liquid. Aluminum has an affinity for delta ferrite and segregates delta ferrite instead of going to liquid. If you enrich delta ferrite in aluminum, and if the aluminum concentration goes beyond critical limit, the thermodynamically delta ferrite cannot transform to austenite and upon subsequent cooling. So we end up stabilizing delta ferrite at the fission boundary when the solidification begins, when by nucleating delta ferrite, the aluminum partition towards delta ferrite, and thereby stabilizing delta ferrite at the fission boundary. The width of these delta ferrite zone in the fission boundaries as a function of again the thermal gradients, as well as a cooling rate that is actually prevailing in the during welding. And generally in gas metal arc welding, GMAW welding, the delta ferrite layer is more, and in laser beam welding and in resistance spot welding, these delta ferrite layers decrease significantly because of a very steep temperature gradient, and there is not much time for aluminum to partition to stabilize delta ferrite. So these are the important roles of the silicon aluminum play. We will move on to the other alloying elements which are present in the advanced size and steels, which are actually commonly there. For example, carbon. So what does carbon do during welding? And we look at the effect of carbon during solidification, and the other alloying elements which are considered detrimental for welding. For example, phosphorus. You all already learned that phosphorus is also added in some of the advanced size and steels, especially to stabilize retained austenite. Phosphorus can also be used to a certain limit, because phosphorus also has an effect on cementite stabilization. It also destabilizes cementite, similar to what silicon aluminum does, and phosphorus also very effective solid solution strengthener. So for a steel making point of view, to generate microstructure, phosphorus can be used to a certain extent, but phosphorus is extremely bad considering when you consider the welding, because phosphorus aggregates to the line boundaries, interdendritic boundaries during solidification, and we will see how the segregation happens and how we can avoid the detrimental segregation of phosphorus in this class. Okay. So if you look at the the conventional chemistry, as I already explained, we can make with varying amount of carbon, is ranging from say 0.05 to 0.2 and thereabout. And so I am going to show you an example of 3 cases where the effect of carbon and phosphorus during welding can be seen significantly, and understand the behavior of these elements during welding. So if we consider an example case in advanced high strength steel, where we have 3 chemistries. Say for example, steel 1, which is known as steel CP. So it has a carbon concentration of 0.07 and phosphorus of 0.08. And in the second case, in 2CP, where we have a double amount of carbon, okay, and the phosphorus being the same. And the third conditions, so we will see the carbon concentration similar to what you have it in the first case, steel CP, and phosphorus is the same, but we added some amount of boron, because we also seen in the previous lectures, boron is also added in some steels to increase hardenability, especially in hot stamping steels. Boron is very much preferred in order to increase hardenability. But boron can also play a significant role in grain boundary diffusion of the alloying elements. How we will see in subsequent slides. So if you can, the example what I am going to show you is in a welding behavior of 3 steels, phosphorus of 0.08, and steel 2CP, we have a double the amount of carbon, and all other alloying elements are the same. And steel CPB, and we have a carbon concentration similar to CP, but we added about 30 ppm of boron. And we keep all other alloying elements same in all these 3 steels. So by comparing steel CP and 2CP, we can clearly see the effect of carbon on the weldability, on the properties of the weld. By comparing CP and CPB, we can see the effect of boron addition on the weldability. Okay, so now from these examples, we can understand the role of alloying elements clearly during welding. Right. So we will move on to the first the phase diagram. So the first understanding we will have to make when you want to understand the elemental behavior is the solidification mode, how the weld pool solidifies. And so when you cool a weld pool to subsequently room temperature, right? See, the mode of solidification is extremely important, because that is going to determine the segregation behavior of the alloying elements, especially the alloying elements which partition towards liquid. So if you look at the example I showed you, the 3 chemistries, and we have 2 carbon concentrations. So one is 0.07, the other one is 0.14 carbon concentration, right? So the steel CP, if you look at the solidification sequences, of course you have inclusions already formed. Okay, so that goes without saying. When the liquid is cooled to below solidification temperature, and if your carbon concentration is say less than say for example an peritectic reaction temperature. So what will happen first in this case, we will have a liquid solidifying first into delta ferrite, and then because of the low carbon concentration, so you will have a complete solidification of liquid into a delta ferrite, and you will have a single phase delta ferrite forming. Whereas if you increase the carbon concentration, and you will first have a liquid solidifying delta ferrite, and subsequently the mixture of liquid and delta ferrite will transform into an austenite by a peritectic reaction. So the solidification mode have significantly have an effect on the partitioning behavior of carbon. For example, if you have a direct solidification delta ferrite, and so your partitioning of carbon to liquid will be maximum, because the solubility of carbon in delta ferrite is much more smaller than the solubility of carbon in austenite. So when a liquid solidified directly in delta ferrite, your liquid will be enriched in carbon given by the liquid carbon in liquid line. Whereas if you have an epitectic reaction, so obviously when a liquid solidifies in delta ferrite first, and then subsequently this mixture of liquid and delta ferrite will transform to austenite. So then yeah, because of the higher solubility of carbon in austenite, your liquid carbon segregation liquid can be decreased. So the solidification mode has a significant role in the carbon partitioning in the unsolidified liquid in the solidification. And so when you have a solidification directly to a complete delta ferrite, when a microstructure becomes 100% delta ferrite and subsequently delta ferrite transforms to austenite, and you may expect a larger segregation of carbon in liquid, which is when during solidification. So in this case, now we have two chemistries where we have an 0.07 weight% carbon and 0.14 carbon. So you would expect the steel CP would completely solidify into delta ferrite first, and then subsequently delta ferrite will transform to austenite. Whereas in steel CPB, the solidification is directly first will be in delta ferrite, will be nucleating, liquid plus delta ferrite would transform to austenite by a peritectic reaction, and subsequently liquid and austenite will have an equilibrium when a peritectic reaction completes. And we will see the solidification behavior of Whirlpool using an high temperature camera, where we can understand very clearly the solidification mode of a Whirlpool. So I am going to show you in a video. And so where the actual solidification microstructure evolution was captured using a high temperature camera, which is known as laser confocal microscopy, where we impose a well thermal cycle onto a liquid pool, and we observe the solidification behavior of a Whirlpool with a chemistry similar to in dual phase steel chemistry. So what you see in this video is the first thing you notice is this guy. So that was actually an inclusion. So I will go back again. So these guys, what you see over here, so that is the inclusion, and inclusion has formed already even before solidification has begun. And what you see over here, this is your heat affected zone, and this is your fusion boundary. So the moment you have a solidification, so you will have first delta ferrite nucleating, and it is going from the fusion boundary towards liquid, and what you see over here, the reaction is the peritectic reaction. So you will go back here. So you have an delta ferrite nucleating, and you have an dendritic solidification going towards the well center line, and then the moment you have an sufficient undercooling, you will have a delta ferrite and liquid interface transforming into austenite. Now the liquid will be growing, will be solidifying directly into austenite after the peritectic reaction. So now the important things you need to understand here in this solidification is, so when I have solidification begin, so how the alloying elements partitioned to these the boundaries of the grains when you are solidifying, and subsequently in how the carbon is also pushed towards the untransformed liquid. And because the carbon concentration of liquid is always higher than the solidifying products, the carbon would tend to segregate towards the unsolidified liquid, thereby enriching the liquid during solidification. So if you look at it in this solidification mechanism, so you will have an partitioning of carbon to the unsolidified regions at the interdendritic boundaries, as well as liquid is solidifying at last. So now we will see in a simulation, so we can also understand how these alloying elements partition during the solidification by simple calculations. So if you look at this slide shows the computer simulations of solidification process, what I showed you in real life. So in this video, and we can also create in a computer the solidification of an dendrite. What you see over here is the actual microstructure, where you have so initially to begin with you have a liquid which is red in color, and we have a delta ferrite, and the delta ferrite is solidifying for steel CP, where we have a solidification is first to completely solidifying into delta ferrite, and then subsequently delta ferrite will transform to austenite upon further cooling. And during this process we can also simulate the partitioning of carbon, for example, and phosphorus, and understand how the carbon atoms migrate from the delta ferrite region to the unsolidified liquid. So here you can already see here, now we begin with the carbon concentration of 0.07, but when the solidification is progressing, carbon migrates to the unsolidified liquid, and thereby the carbon concentration gets enriched in the liquid which is not solidified, and subsequently the carbon concentration at the dendritic boundaries, when it develops and these regions, carbon concentration can go as high as even 0.4. So even though you have a bulk carbon concentration of 0.07, and because of the carbon partitioning during solidification, and lead to a severe enrichment of carbon atoms in the unsolidified liquid, and thereby the grain boundaries, dendritic boundaries in this case, getting embrittled. And the behavior can also be observed for phosphorus as well, because phosphorus also segregates in the similar way of carbon, and even though we have a very small amount of phosphorus, 0.08, you may still see a severe phosphorus segregation at the interdendritic regions, and as well as the regions which solidify at the end. So if for a bulk phosphorus concentration in the liquid of 0.08, you may end up having enrichment at the dendritic boundaries close to the level of 0.7. So that means that so in this solidification behavior as well, so if you look at it now, you would end up having a segregation at the interdendritic boundaries, as well as when the regions which are solidifying at the end in carbon and phosphorus, the tune of 0.4 to 0.7 respectively. So that means that even if you start with a very low amount of carbon and phosphorus in liquid, which is a bulk carbon concentration and bulk phosphorus concentration, and locally at the grain boundaries and dendritic boundaries and the well center line, you may expect a very strong segregation of carbon and phosphorus. And you all know that if you have 0.7% of phosphorus, and you have an extremely brittle grain boundary as well as carbon as well. So now we will see steel CP again in steel CP's case. And so first we have the complete solidification of liquid into delta ferrite, and then subsequently delta ferrite transforms to austenite, and you may expect a very severe segregation in this case, because the delta ferrite carbon concentration is much less than liquid carbon concentration. There will be severe partitioning of carbon from delta ferrite to liquid when it is solidifying, whereas in steel CP, as already explained, steel CP still 2CP, where we have 0.14 carbon concentration, and you expect an peritectic reaction. Okay. And because of peritectic reaction, you may expect locally the carbon concentration changes. So in this steel, the solidification mode is first is you are having a liquid plus delta ferrite, and then subsequently this would transform into the austenite even when you have a liquid in the material. Similarly, you can understand the segregation behavior. So you have now double the amount of carbon concentration in the bulk. So with that bulk carbon concentration, you may still expect a segregation up to 0.7, and phosphorus up to say much higher than you see in steel CP. So this is very bad, right? So the carbon partitioning and phosphorus at the well center line and the grain boundaries would make the grain boundaries very brittle. And can lead to an embrittlement, and we will see in the subsequent slides and how this embrittlement can lead to the deterioration in the mechanical properties. And now we will compare in one case where so we froze the microstructure at a temperature about 1771 Kelvin. So the solidification begins somewhere around 1800 Kelvin. and we froze the microstructure at 1771 Kelvin, and we will see at one point where we have still liquid is present on these regions, for example at these boundaries. And if you look at the phosphorus concentration variation along this line, so along this line, if you look at the phosphorus concentration variation, and you can see that locally the phosphorus can go up to 0.4%. That's what I explained in previous slide. And this is due to the partitioning of phosphorus from the delta ferrite towards solidifying liquid. Right. So to begin with, the entire liquid has the phosphorus concentration of 0.08, and because of the partitioning of phosphorus from the liquid to the solidifying liquid, and can lead to the enrichment of phosphorus at the last solidifying liquid regions, and those regions can be enriched in phosphorus. For example, in this case, the phosphorus concentration at these boundaries can go as high as 0.48%. So now what happens now if you look at the steel with an 80 ppm of boron, 30 ppm of boron. So what does boron do? So what we see that this is in a steel CPB where we have a 30 ppm of boron. So what happens with the presence of the 20 ppm of boron, and you already see that in the amount of phosphorus at the dendritic boundaries decrease some amount. So previously without boron, you see that phosphorus concentration can go up to close to 0.4, whereas by adding 30 ppm of boron, the phosphorus at the dendritic boundary is already decreasing to about 0.1%. So what does it mean then? So the addition of boron favorably reducing the segregation of phosphorus at dendritic boundaries, and the boron atoms once they segregate at the solid liquid interface, and it stops the phosphorus atom to coming to the boundaries. The boron diffusion of boron is much rapid than phosphorus. So boron atom can readily diffuse from the delta ferrite to the boundaries of solid liquid, and then once you have the segregation of boron at the boundaries, and it subsequently stops the phosphorus atom coming to the boundaries. So therefore by adding boron can positively influence the segregation behavior to our favor, where it can reduce the phosphorus segregation at the solid liquid interface, and subsequently the grain boundary segregation of phosphorus can be decreased significantly. So this can be seen for example comparing these two. So you can already see the steel with 27 ppm 30 ppm of boron, the maximum phosphorus segregation is 0.35 at one point, whereas you would expect higher phosphorus segregation and without boron. So boron is already effectively favorably modifying the phosphorus segregation, and can lead to a change in mechanical properties, because once you have reduced the phosphorus segregation at the boundaries, then you may already reduce the brittleness of the microstructure. So you see there are some scans to confirm what I showed you. So if you have only carbon and phosphorus without any boron, you see the segregation. This is a measurement carried out on a real weld. So this is in a spot weld. What you see over here. So this is your this weld nugget. What you see here, and then when you look at the elemental mapping along the center line, the black arrow, what you see over here, and you would see the interdendritic regions. The phosphorus segregation can be seen to as high as 0.4, as I showed you in the calculations in the video. In steel with the boron, with the 30 ppm of boron, you already see the red, the phosphorus concentration can decrease already even less than 0.3 at locally. So even much less than 0.3 you can see. So the boron is indeed effectively reduce the phosphorus segregation. We can play around now with the chemistries to avoid the formation of the brittle grain boundaries. So you can also see the same measurements observations using a secondary ion mass spectroscopy, where you can see the elemental distribution clearly. So if you look at at central line, you see 1 point boron segregation. So once you have a boron segregation at the location, and you see a depletion of phosphorus concentration other locations close to where you see an boron segregation. So that means that boron indeed stops the phosphorus atoms coming to the unsolidified liquid, thereby the phosphorus induced grain boundary embrittlement can be avoided. So you will see the comparison between the hardness of the wells. And if you look at it, because comparing the steel CP and CPB, and we have a similar carbon concentration, phosphorus concentration. So only difference what we have is in CPB about 27 ppm of boron, right? And the boron additions may influence the formation of the martensitic transformation and subsequently cooling to room temperatures, but you would not see much significant change in the hardness values. So what you see over here is the hardness variation over the length of resistance spot weld nugget. What is shown over here in the top image, how the hardness variation happens when you move from one side of the base material to the other side of the base material. You see the weld has a significant increasing in hardness, and because of the formation of complete martensitic microstructure. And comparing two steels, like for example steel CP and 2CP, and we have a double the amount of carbon concentration, and that can lead to a significant increasing in the hardness of the microstructure, because the carbon is also very effective solid solution strengthener, and you may also have martensitic microstructure with rich in carbon compared to steel CP, and you expect an increasing in hardness. That's what you see over here. And whereas steel CP and CPB, and you don't see much variation in carbon concentration, because all other compositions, the alloying elements are the same except boron. So we look at now the mechanical properties of the wells of these three cases, and we carried out the tensile shear test, and I already explained how we carry out this test during resistance spot welding lecture. So basically we make a weld nugget in an L flanges, and then we pull it with a tensile load and observe the load to failure as well as the plug ratio. So recall what is plug ratio, right? So plug ratio is the weld nugget diameter over the plug size after failure. So you see already the steel CPB have a very good plug ratio. So if plug ratio is close to 100, that means that you have a complete plug failure. And if your plug ratio is 0, then what happens? Then it has a complete interface failure, right? So that's what I explained in previous resistance spot welding lecture. You see, so as a function of welding current, the Imax, the maximum current, you would see that complete plug failure is observed for steel with boron, and 30 ppm of boron, whereas steel CP has a mixed mode failure, and where plug ratio is not really acceptable, whereas in CPB has a very good acceptable failure mode. But still 2CP, you see that there is no plug at all left. So you can imagine that the failure will be completely the interface failure. So this is what happens when you look at the plug sizes. So in steel CP, the failure is in a partial plug failure. So where we have what you see over here is a weld nugget diameter. You see here, And then if you look at the cross section view, so if you take a cross section somewhere over here, and then I look at from this direction, and what you see over here is in steel CP, the crack formed at the interface, the pre-air interface before welding, and then it propagated along the weld center line, and then failure happened once at the middle of the nugget. It also behaved the same from other side, starting from the weld center line, and a crack nucleating from the pre-air interface. So pre-air interface, how does it look like? So if this is your weld nugget along the cross section, so when you make a cross section along this plane, so along this line, for example, and it will look like this. So this is your pre-air interface, and this is your weld nugget. So crack nucleated from this location and propagated along the weld center line, and then failed. So leading to a partial plug failure, and this is very typical behavior when you have an weld center line segregation. So this center line is the loss solidifying region in resistant spot welding. So obviously you will have a segregation of phosphorus and carbon along this weld center line. So when you have an brittle weld center line, so when you test it in a tensile testing, as I explained in previous graph, so you have a crack nucleated and following weld center line and subsequently failing along the weld center line, leading to a partial plug failure. And if you have very severe segregation along the weld center line, and you will have a complete interface failure, okay, where you open up the welded plates as it was before welding. So that means that there is no weld nugget remain on the weld regions, and you will have a complete interface failure. And when you have a very strong segregation, obviously in tool CP case, and the carbon concentration really high, and you would segregate weld center line completely with carbon, because that is the region which solidifies at the end, and that can lead to a complete interface failure where the plug ratio here it is 0. So because there is no plug remaining in the weld, and here we see some plug remained, but it is not still acceptable. The acceptable case is the case here, where we added the 30 ppm of boron, 20 ppm of boron, and you see the failure is completely in the heat affected zone elsewhere. And if you look at it, the entire spot weld nugget is remain attached as it was before tensile testing. So that means that with the addition of boron, the center line segregation of phosphorus is minimized, and so when you have an tensile testing, we found that the crack is actually formed along this edge and then propagated in the heat effect zone itself. That means that the weld properties are even better than your base material property. And this happens because we managed to avoid the phosphorus segregation along the weld center line, and by adding the boron, and that can lead to improvement in the mechanical properties of the weld. So therefore, with the addition of boron, we can say that the phosphorus segregation is reduced at the weld center line, and leading to improved in the mechanical properties. So to summarize, so we looked at the centerline segregation of the alloying elements, mainly carbon and phosphorus, and why they are detrimental during welding. And it is important to understand the solidification mode of these steels based on the carbon concentration. If you have a low carbon, you may expect complete delta ferrite solidification. Subsequently, delta ferrite can transform to austenite, and this can lead to a segregation of liquid, carbon in liquid. And so when you have peritectic reactions, obviously you may also have austenite forming from liquid to plus delta ferrite mixture, and you may also locally change the carbon concentration of liquid because of this reaction. And we looked at an solidification microstructure in situ during solidification, how the dendrites evolve and how the solidification progress. And we looked at the carbon and phosphorus atoms migration during solidification via a computer simulation. And we also studied about the role of the contemplating alloying elements, for example boron. So how boron can stop the phosphorus segregation at the well center line, and because of that mechanical properties of the wells can be improved significantly in advanced iron steel.